So we talked in class about the advantages of preload on a bolt. When you tighten a bolt, there's a few reasons that you want to tighten past the point where the head of the bolt just barely touches the material. You want to go further than that because A, you're trying to hold the two parts together. You're trying to squeeze the material together. If you don't tighten it anymore, then the bolt is loose in there and it's not squeezing the two pieces together. Any amount that you pull is going to try to separate these two pieces. That's not good. You don't want those to separate. Another reason is that you want friction to keep the bolt in place. When you tighten it and you preload the bolt, you actually tension the bolt. We'll see that. We'll talk about that in just a second. But you put tension in the bolt. That creates pressure between the male threads of the bolt and the female threads of the nut, and that pressure requires friction, adds to friction, so that if you try to unscrew the bolt, it's going to be harder to do that the more that you've screwed it in. The more that you tighten the bolt, the harder it is to undo it. That's obvious, right? And so the more friction you have, the harder it is to unscrew the bolt, which is a good thing. You don't want the bolt to unscrew on its own. The final thing was that it turns out that when you add preload to a bolt, then any additional load that you apply at this interface, if I try to separate these, so with the force F, I'm going to say it's like some distributed force, but the total force is F that's trying to pull these two things together. It's F on both sides. I'm pulling the top plate with force F. I'm pulling the bottom plate with a force F. When you do that, it turns out that let's say that this were time varying, if this were a sinusoid, F equals F naught sine omega t. Well, if you don't preload the bolt, then all of that force becomes tension in the bolt. Okay, and so the tension in the bolt varies between whatever this force's minimum is and the maximum. Let's say it's actually, so of course, F naught sine omega t, if that force was sinusoidally varying, if you push on the two parts, that's not going to be tension in the bolt. But the tension in the bolt is going to be just the positive side of that sinusoid. So the tension in the bolt through time is going to look like, like that. It's not going to go negative because when you push on the two materials, it's not going to push on the bolt. So it's going to wait a little while and then it's going to come up again. But the point being is that you've got this large amplitude here. There's a large amplitude stress on the bolt. But it turns out that if you do the same thing but you've preloaded the bolt, then you're going to get a mean stress in the bolt that's higher because of the preload. We'll talk about that in a second. But you're going to get a smaller amplitude on top of that. Well, I guess I can, it's going to be the same period, and then it's going to go back to normal, and then it's actually, no, I think you're actually going to see the sinusoid here. But the point being is that it's a smaller amplitude stress. Okay, so that's one of the advantages of preload. So let's see why that's the case. That's what we're driving up to. What is the effect of preload on how much of this force that the bolt sees? Okay, so we need to consider what happens when you preload a bolt. Preloading means that I've torqued it to a certain amount. We looked in class, there's an empirical relationship between the torque that you apply and the preload that you get. You could apply the theory that we learned about for power screws, but it turns out that it's maybe simpler for bolts to just look up the preload value that you get from a certain torque. It follows a relationship of the form T equals some constant K times the diameter of the bolt and times the Fi. And so the Fi that you get, the force, the preload, is just the torque over the K for the bolt and D. And this is something that's usually in a range of 0.2. Again, you could get this relationship, that the torque force relationship is just the same idea when you're looking at power screws as for fasteners, but it turns out that for fasteners it's nicer to use this just simpler relationship where K is often around 0.2. That's the diameter of the bolt and that's the torque you put in. Okay, so why does this happen? Why do you get this preload? Think about as you turn the screw, as I twist it. Well, you know that the top head of the bolt is not going to move down any, unless it's always going to stay. The top face of the screw's head is always going to be in contact with the top face of the material. So maybe the material will squish a little bit, but those two things will always be in contact. On this side, though, you might find that as you screw it in, the bolt is going to appear to elongate. It's going to appear to grow past the end. You've tightened a screw before. It's going to go further and further past the nut. Even though this top face is where it was before, you're going to see the threads start to appear down there. That means that the bolt has to have gotten longer. The bolt got longer as you screwed it in because the threads, it's just a kinematic relationship. Those bottom threads, you twist the bolt, it has to go. And so it pulls on the bolt and it stretches it like a spring. And the material compresses at the same time. So the bolt stretches like a spring, the material compresses. So let's model what that looks like. I'm going to erase this. So we need to let's pretend, this is a symmetric problem, so let's just look at it from the center line here. The bolt I'm going to represent with a spring of stiffness. I'm going to call it KB for the stiffness of the bolt. And then here's the top head of the bolt. And it's pressing on the material. So this is the bolt here. And it's pressing on the head of the bolt, it's pressing on the material. I'm going to consider the material to be another spring. And that spring is actually already in compression. Km for K of the material. And when I pull with a force F, this is what my force looks like. And so since this is a symmetric problem, we're just going to consider the top half. If you want, you can think of this as being fixed on the bottom here. And when I pull, that's going to tend to, increase the length of the bolt. And because the bottom half of the bolt and the bottom face of the bolt's head and the top face of the material, since they're always in contact, that's going to tend to compress the material less. When I pull on the material, I'm going to tend to stretch the bolt, and the material is not going to be compressed as much as it was before. So it's going to move upwards by a certain amount. We'll say delta when that happens. Okay. So let's figure out what the relationship is between those forces and all that stuff. So let's say we know the stiffness of the bolt. We know the stiffness of the material. The stiffness of the bolt, it's in the book. You can find the stiffness of the bolt by basically saying what's the cross-sectional area, what's the Young's modulus, what's the length. Okay, from those things we can figure out a stiffness. The material itself, what's the stiffness of that? That's a little bit tougher. I mean, one possibility is that you could say, all right, well, I'm going to compress all this material here. So it's basically you're compressing this annulus of material, this ring, this hollowed out cylinder of material. And so what's the stiffness of that material? In reality, it's actually going to kind of be sort of a cone shape where the stress goes through. And so it's going to be a larger stiffness than what you'd expect from just a cylinder. But let's say that we know these stiffnesses, all right? We're trying to find out what the effect is of the force on delta given these stiffnesses. All right, if you know those stiffnesses, that are two springs acting in parallel. So the relationship delta is going to be the force divided by the total stiffness of those two things springs in parallel. And the two springs in parallel is KB plus KM. Okay. So again, that is the displacement that it's going to see. Whatever those stiffnesses are, whatever that applies force, that's how much delta is going to be. And you might think, actually, and this is where I have the spring here, well, this material is in compression. If I pull on it, it's not going to resist my pull, is it? As long as these materials in contact, it will. I say this because you think about this spring, and this is a tension spring, okay? If it's stretched to here and I try to pull on it, oh, it's not resisting me, right? It's trying to help me. Well, think about it when it's preloaded with gravity, right? Then this becomes a spring in either direction. The force is proportional to the displacement from the nominal length. The force is proportional to the displacement from the nominal length. Okay? In the same way, when the spring, this bolt is preloaded, or when this material is preloaded, it's squished. If I try to pull it upwards, it's going to resist that. It's going to resist that, and it's going to be proportional to the stiffness of the material. All right, so the displacement is equal to the force divided by the total stiffness. Something else that you know about the displacement, well, the displacement is the same as the displacement that you would see if you thought about what is the additional tension that you're adding to this bolt. What's the additional tension that I'm adding to the bolt? So the tension that I'm adding to the bolt divided by the stiffness of the bolt, that has to be equal to that too. Actually, I think in the book it calls this FB. This is the additional force that's going into the bolt. No, I think it calls it PB. Yeah. So the force that's actually, so this force is applied to the system as a whole. It's applied to here. It's actually applied to the material, but how much of that does the bolt actually see? It's PB. And that divided by KB, the stiffness of the bolt, that has to be equal to delta. Something else is, well, how much does the material see? It sees a certain amount, PM. It's originally preloaded by an amount Fi, and that's going to be reduced by PM. Well, PM divided by Km, the stiffness of the material, that has to be equal to delta 2. Okay, so this relationship here is going to tell us how to get what the force, the additional force in the bolt is. Notice, well, let's solve for it, okay? So the force in the bolt, PB, that is equal to whatever force is applied times KB over KB plus Km. So what this is telling us is that when we pull on it, as long as the bolt is preloaded, such that this assumption that when you pull on it, both the bolt and the spring and the material are kind of acting as springs resisting displacement, then the additional load in the bolt, the additional stretch in the bolt in addition to the preload, is going to be not equal directly to just F times 1. It's going to be equal to F times some constant. And this constant we call C. It's the stiffness coefficient, the joint stiffness coefficient called C. And this can be less than 1. If it's small, think about it. The additional load in the bolt, we've got the total load in the bolt, total force in the bolt, FB, is equal to the sum of Fi, the preload, plus whatever this additional PB is. So if this is a small constant, then the force in the bolt does not change very much, even if you have a large F. Even if this is a big sinusoid, it gets multiplied by a small constant when you're considering the total force in the bolt. And this total force in the bolt is what you're going to use to figure out whether the bolt's going to break or not. So in fatigue situations, that's beneficial, lower amplitude stress. All right, why is it going to be smaller than 1? Well, it has to be, because KB, these are both positive numbers. This can only be bigger than the numerator here, so this is going to be smaller than 1. And it turns out that the bolt, because it's smaller in diameter, and it's the same length as all this material, but smaller in diameter than this cone of material, Km is usually going to be actually bigger than KB. So this is often going to be, on the order of 0.25, something like that. All right? Let's figure out what the additional force in the material is, PM. Well, PM, let's think about the total force in the material. The force in the material, it's initially a negative force. It's in compression, so it's negative whatever the preload in the bolt is. But we're talking about adding whatever this is, whatever tension is coming PM. Okay. Well, it's KB over KB plus KM, or excuse me. So So PM, if we were to solve this, PM over Km equals delta, or is equal to that, then PM is equal to F times Km over Kb plus Km. That's how much the force in the material gets reduced. And that's going to come into play later. And it turns out that this is equal to just 1 minus c. We can see that. Let's go ahead and see that. I'm going to show that so 1 minus c is kb over kb plus km. That's going to be equal to, I'm going to multiply by kb plus km on both sides. Kb plus km over kb plus km minus kb over kb plus km, so common denominator. Kb minus kb, it's just km on the top. Km over kb plus km. Okay, so that's just to show that this is 1 minus c, and that's going to be important later. Okay, but what we have here is a relationship that the total tension in a bolt, the total force in the bolt, is equal to the preload plus some constant c times whatever the additional whatever that applied load is. And because c is often smaller than 1, this being the time varying part of the stress, the stress amplitude can be smaller than it would be otherwise, which reduces concerns of fatigue in bolts. So that's one of those third reasons why fatigue in bolts, or why preload is a good idea.